Welcome to an authoritative guide to the architecture, performance, and use cases of the CPU versus the GPU in the age of AI. AI has fundamentally changed computing rules. The focus has shifted from clock speeds to parallelism, efficiency, and scalability. The CPU is the operations brain, a general-purpose processor designed for sequential processing and complex instructions. It excels at logic, decision-making, and system control, aiming to minimize latency for individual tasks. CPU architecture is designed for speed and flexibility, featuring complex cores and deep cache hierarchies to minimize memory access latency. This design prioritizes completing individual tasks as quickly as possible. The GPU is the engine of parallel computation, originally for graphics rendering. Its architecture is built for massively parallel processing, with thousands of simpler cores, optimizing raw computational throughput for large datasets. GPU architecture is designed for massive parallel throughput. Thousands of simpler cores simultaneously execute the same instruction across many data points, making it a perfect match for matrix multiplication in AI. The architectural divide is between the CPU as a sequential expert and the GPU as a parallel factory. The CPU uses few powerful cores for low-latency tasks, while the GPU uses thousands of simpler cores for large-scale math operations. Matching the processor to the AI workload is key. AI training requires massive parallelism, making the GPU superior. AI inference can run on CPUs for real-time edge scenarios or GPUs for high volume, depending on the need. Performance is a trade-off between latency and throughput. CPUs minimize latency for single tasks, while GPUs maximize throughput for large data batches. The workload dictates the necessary priority. The economics of AI computation involve several factors. GPUs offer higher performance per watt for parallel workloads. CPUs have lower upfront costs. However, GPUs can reduce total cost of ownership by completing jobs faster. In practice, CPU-dominant scenarios include AI workflow orchestration, data preprocessing, and real-time fraud detection. GPU-dominant scenarios include training large language models, computer vision, and scientific simulations. A singular approach has inherent limitations. CPUs are inefficient for large-scale matrix math, leading to bottlenecks. GPUs are inefficient for sequential tasks and I/O management and require a host CPU. Architectural synergy is the dominant model for modern AI. The debate focuses on how CPUs and GPUs work together. The CPU acts as the control plane, while the GPU is the powerful computation engine. The cloud and enterprise blueprint for AI relies on CPUs as the foundation for the operating system and orchestration. GPUs are provided as specialized on-demand accelerators, maximizing utilization and cost efficiency. The future is a cooperative, heterogeneous system. The trend is towards specialized accelerators, like NPUs and TPUs, alongside CPUs and GPUs. Understanding this cooperative model is key to building future-ready AI infrastructure.